And so I don't know which one is worse. But fortunately, the room is small. Thank you.
I never even know there was a drawer under there. Somebody stuck it in the other drawer.
Well, I knew, but I assumed we know better. Thank you so much.
Also, I think these curtains have been open since World War II, but they probably opened. Next time I'll try to let some more light in here.
Okay, I was about that commercial for cell phone. I was going to ask, can you hear me now? But no, I guess you can. So first, it was obvious. You all noticed that last time when it comes to bond dissociation energy, alkyl always is weaker than vinyl carbon gas. This is something that in those I gave you correct numbers, that when I was putting the sign, instead of putting alkyl bond dissociation energy is less, I put more, so I want to make sure that you check your notes. Now, last time when I started, they were talking about physical properties of alkenes, which are very much similar to alkanes. They are water insoluble, they are nonpolar. Any compound that is nonpolar generally has low boiling point. Now, that being said, other physical properties, boiling point, melting point. When it comes to boiling point, these are something that we have experimentally observed. When it comes to boiling point, don't forget, boiling point also depends on intermolecular forces. Now, how about cis and trans? Between cis and trans, which one would you expect? Keep in mind, I'm talking about intermolecular forces because there is no other forces. Intermolecular forces between cis and trans, which one would you expect to have higher boiling point? Or are they going to be the same?
I guess trans has higher boiling point. No, wait. Cis has higher boiling point.
Cis has higher boiling point. The reason that cis has higher boiling point, you may remember such a thing as hyperconjugation. Is that right? When it comes to hyperconjugation, the alkyl group is something that we call it electron pushing or electron donating group. So what will happen? In cis, the groups are pushing electrons both from the same direction. They don't cancel each other. So when it comes to dipole moment, the dipole moment of this cis is slightly polar. It has very small dipole moment. Whereas trans is 100% non-polar. So because trans is non-polar, the boiling point of cis, which is slightly polar, is a little bit 2 or 3 degrees, not huge, I want to know that. 2 or 3 degrees is higher than its diastereon. Now, when it comes to melting point is exactly opposite. By being exactly opposite, and this time it is significant. This time it is significant. When it comes to melting point, cis has smaller, lower melting point than trans. Why this is the case? Well, melting point not only depends on intermolecular forces, also depends on packaging and packing. When it comes to trans molecules, due to their shape, you can pack them nicer. You know, I will compare those as senior citizens, the analogy similar to shopping carts. Have you seen that they will put all of those shopping carts? And between you and all, I have difficulty to pull them away. But I am lucky because I am living in Davis, and my face is recognized, believe it or not. It never has happened that I go to any grocery and at least one or two of my students are not around when I'm trying shopping. And they know the story. Guess what? Before I even get to front door, a shopping cart is waiting for me. And I'm not making this up. 3 days ago, I was in Trader Joe. The other student not only had a shopping cart, also put a basket inside it. So I could choose depending on my, shopping plan, which truly I am grateful. So keep in mind, trans molecules are those shopping baskets, shopping carts. They stack nicely. So because they stack nicely, it takes energy. You heard my story. It takes energy to pull them apart when it comes to melting. But cis molecules are like shoeholes, They are stacking on top of each other. They don't pack. Because they don't pack, it doesn't take that much energy to break them apart. Now that being said, probably nowadays you see any food package you buy, there is part of the note on it, no trans fatty acid, or no trans fat. Am I correct? Let me tell you, Mother Nature does not make trans carbon double. Mother Nature makes only cis. So that's the difference between fats and oil. Both fats and oil, they are large hydrocarbon section with ester group. So ester is common denominator. It's exactly the same ester. The only difference is the chain. Fat generally are saturated carbon chain, whereas oil are unsaturated. And the more pi bond they have, the more unsaturation degree, guys. The more unsaturation degree means what kind of melting point? Lower melting point. And that's why you will see, a brand of olive oil in their ad. They take a glass of olive oil and they drop tomato inside it, put it in freezer. Does it freeze? No, because obviously it has too many unsaturated. So unless you bring the temperature to minus 30, 40, which freezer generally is minus 20, they will not freeze, guys. So I want you to know, freezing point and melting point not only depend on molecular shape, molecular structure, intermolecular forces, they depend on molecular shape. boiling point is only a function of intermolecular forces. So that's as physical property. Now I want to talk about synthesis of alkenes. That in order for us to predict major organic products, I know probably you are familiar that when you are doing organic reactions, the chances are you will get more than one product. And the question is, if I am getting two or more, which one is major organic product? Because commonly, especially on exam, I'm going to tell you, I always ask for major organic product. Because if I ask for all possible products, they would never ever have enough time to finish grading and submit your first grade by the end of the deadline. So I always ask for major organic product. Now this is something that it is important before I talk about synthesis, we talk about relative stability. Because relative stability determines whether E or Z would be expected to be major organic product of E2 elimination. Now you have already seen relative stability in alkanes. To be more specific, which class of alkanes, guys? You were talking about relative stability. Cycloalkanes. When it comes to cycloalkanes, which cycloalkane is expected to be the most stable? Hexane, absolutely. So you have already talked. And when you talked about relative stability, it was based on what kind of experimental observation, because these are based on experimental, guys, nothing else. So based on what kind of experimental observation, we learned cyclohexanes are more stable than any other ring size. Heat of combustion. We can use the same thing, but with alkene we have one other information that, as a matter of fact, is more useful. Now, I want to let you know when it comes to energy, the energy of a chemical reaction, heat of a reaction, is an indication of the stability of the compound. The higher heat of the reaction means, is your reactant more stable or less stable? Less stable. And because don't forget, the trend is down to earth. Is that right? So more stable are down to earth. When you do reaction, they produce less heat. Less stable, they are high flyer, unstable. So when they react, they produce more heat. So we are doing three reactions. A, B, and C. Of these three reactants, which one is the most stable? Obviously, C. So this is something that you have to be careful. Of course, when we are talking about heats of reaction, do you expect the sign be positive or negative? Kinetic reaction. For heats of reaction, do you expect sign be positive or negative? You expect negative. Right? Remember, spontaneous reaction, they are exergonic, negative sign. So, negative only tells you yes, the reaction occurs. Positive means forget about it. So if I'm talking about a reaction, guys, don't use the negative in order to say, obviously, between negative 27 and negative 80, just numbers. Between negative 27, negative 80, which one is smaller? Negative 80. That, are you going to use those negatives when it comes to heat of reaction? No, because they only tell you whether it is endothermic or exothermic. So you only use the absolute number. The higher the absolute number, the less stable starting reactant. Now, when it comes to alkenes, we are using heat of halogenation. The reason that we are using heat of halogenation because we can get same product from diastereomers and also structural isomer. So the fact that product is the same, then it even is more helpful.
Could you repeat the two things you said? You get the same product from what?
Diastereomers and structural isomers, and which I am going to show you in a couple of minutes or less to tell you what I'm talking about. So I was saying that heat of hydrogenation for alkenes is even more efficient than heat of combustion because we are forming same compounds. So the heat of the compound is common denominator among all. So that being said, so it's not surprising that we are going to use heats of hydrogenation. When it comes to alkenes, they do react with hydrogen, but I have to remind you, hydrogen is the lightest gas that reacts. So it's not just easy put alkene and hydrogen together and hope for the best. Anytime we are using hydrogen, we must have catalyst. And it happens that hydrogen has very expensive taste. Any metal that is $1,500 per ounce or higher does the job. Platinum, palladium, those kind of things. So, guys, if you remember, that's fine. If you don't remember, please make sure at least spell CAT, which it means you understand there has to be catalyst. And in the future, I will tell you, if you say CAT, you mean normal catalysts that they are commonly are being used. Beyond that, we have special catalysts. You have to remember them. I will tell you in the future. Now, obviously, we cannot afford that kind of catalyst gas. Because, you know, as a researcher, a professor in his or her lab has certain amount of grant, and truly they cannot afford that kind of elements, especially if they are organic chemists. The organic chemist, I know, our role model is carbon. So that's the reason that you will see commonly, whether we are using platinum or palladium, it happens that carbon helps. So we are lowering the price by using our favorite element, carbon. So this is what will happen Okay, guys, of course, I'm not talking about the other 4 groups. Obviously, carbon always has how many covalent bonds in OK?
4.
4, always. As a neutron, it must have. As a compound that you can isolate, you can market, it must have 4 covalent bonds in any form. So you know the other that I have not put, that's what they are. So we are using heat of hydrogenation to saturate our pi bond. Now, based on that, experimentally we have found I am going to use 3 compounds that they all form the same product. Okay, so obviously the relationship between 1 butene and 2 butene is what, guys? What is the relationship between 1 butene and 2 butene?
Where the double bond is.
What's the relationship? What is the name of the relationship? Constitutional or structural isomer. What is the relationship between cis and trans 2-butene? Diastereomer. You know, if you say a stereoisomer, you will get only 1 out of 4 points, for example. Partial credit, because it is defined, diastereomer, very specific. So, as you can guess, all these 4 will produce same product, which it is. What is the name of the product? Butane. Now, I'm going to give you delta H of the reaction for all of these are kcalody. Generally, when I give heat of reactions, guys, is kcalody and not joules. So I want to be familiar in case I don't give you. Unit energies, I give always kcalody. Cis 28, again, obviously. Trans negative 27.6. Question. From this observation, which alkene is the least stable and which is the most stable? The least stable is?
Trains.
Is the one that you wrote out with all the C's.
Okay. This is, remember I said less heat, more stable. The diagram is still there, guys. So this is something experimental. Based on this understanding, everybody has seen the correction. Am I correct? Because I do need, obviously, chalkboard. So based on this observation, experimentally, based on experimental, again I repeat, based on experimental observation, we have learned least substituted is obviously least stable one. Then mono substituted. Then mono substituted is less stable than di substituted. Now, when it comes comes to disubstituted, yes, sir.
Monosubstituted? Left? Oh, sorry, on the top. My bad. Never mind.
Monosubstituted is less stable than disubstituted. Now, speaking of disubstituted, it won't make any difference whether one gets both substituent and the other doesn't, or cis. So, because cis also is disubstituted. So, disubstituted in any form as either cis or just simply disubstituted. They are less stable than, as you can guess, terans. Oh, by the way, if you are writing, you can just write horizontal just continue, but I just want to keep them for a while. As you would expect, then it's going to be trisubstituted. And most stable is going to be heterosubstituted. So this is a relative stability for non-cyclic alkenes. Now, when it comes to cyclic alkenes, cyclic alkenes, for cyclic alkenes, up to 7-member ring, there is no trans. Up to 7-member ring, up to 7-member ring, only cis. Now, when up to 7, it is not possible to have trans cycloalkene. I will remind you we said pi bond forms when p orbitals are parallel to each other. So due to this required, it's not possible to twist our p orbitals and have pi bond in trans position. Starting 8, we can have cis and trans. But again, because still there is not a perfect overlapping, believe it or not, cis is more stable than trans. (11) and 12 carbon, cis and trans are equally stable. Once you have more than 12 carbons, guess which one is more stable? Guess. Trans. Because now the ring is long enough that the molecule acts like open chain. Okay. So more than 12 carbons, the molecule acts as open chain. Trans is more stable. So these are as relative stability. So with that in mind, now we are going to talk about synthesis of alkenes, which pretty much we are going to review reactions, elimination reactions that you did in Chem 118A, chapter 6, 7, and 9 galleys. So the first that we are going to focus is E2 eliminations. You may remember hydrogenation. Of hydrogen. What we learned in Chem 118A now, X is which element, guys?
Halogen.
I know, but that's what I wrote. Which one?
Chloride. Bromine.
Anything but
Fluorine.
fluorine, okay? Anything but fluorine. So one thing that we learn, when we react a haloalkane with a strong base. Strong base, we mean at least hydroxide or alkoxide. So when we are reacting this with a base, the first time I will use a lone pair electron, but I want to let you know, guys, I am assuming you know your Lewis structures. So when you have a formal charge, negative, you would expect that you lone pairs. In the future, you may not see lone pairs. And on exam, if you miss lone pairs, I will let the PAs do not make any deduction. Because at this point, I honestly believe that you know your Lewis structure. So one thing that we learned, when we are using strong base, we would expect elimination. Okay. So what will happen? This is what we learn. All of this happens in one step. What I mean is two groups are departing. One is proton, the other one is whatever we are calling it as a leading group. And two carbons are going to rehybridize from sp3 to sp2. It has a very crowded transition state. If you go back and review your mechanism, for which I will go in detail in a few minutes anyway. But one thing that we did not, or we may not have covered, is regiochemistry and stereochemistry. These reactions, E2 reactions, first, are not reversible, one-way reaction. Second, they are regioselective. Now, what do I mean by regioselective? Let me take it. So I am taking, obviously, 2-bromo-3-methyl butane. And I am going to react it with a strong base. Common practice is we are using alkyl salts for elimination. I will remind you. Unfortunately, oh no. Fortunately, we do have a periodic table, I didn't see. It's out of my hand. But, yes.
Oh, what did you call that base again?
Sodium ethoxide.
Ethoxide. Sorry.
That's okay. So, elements, alkali metals, you may know, they are the most electropositive elements in periodic table, for which it means any alkali metal you have it in a compound, it must have what kind of charge gas? Positive one. Any alkali metals that you have column one, it must be positive one. So having positive one, it means that the next atom that is bonded to that has to be negatively charged. So this is, whether you see it or not, it's there. When you write sodium chloride, you don't write Na plus Cl minus. You know sodium is cation, chloride is anion. Same thing, no difference. Both of them are ionic, both of them are called salt, A-L-T. Now, that being said, also, you and I know that when we are doing chemical reactions are being done in solvents because ions, atoms, molecules have to have the ability to move around in order for them to collide for chemical reaction. Common practice is the conjugate acid of your base is going to be the solvent. So that is common practice for convenience only. Now, in this case, obviously, you have strong base, you have a secondary hollow alkane, for which it means major pathway is elimination. Not only elimination, it is E2. Now, if it is E2, how many E2 products are possible then? Here. 2. Why 2? Because each neighboring carbon has a hydrogen. And I want to let you know about the vocabularies. The relationship between two atoms that they are bonded together, you know, neighbor. Vicinal. Okay, so when we are talking about vicinal atom, we are talking about the neighbor, the next door neighbor, literally next door, not 2 doors away, not 3 doors away, only the next door neighbor. And the reason that I want, because you will hear quite a few vocabulary that you don't want to get confused. What do you call this carbon? Vinyl. So be careful. Vicinal is not necessarily vinyl. But these 2 carbons are what, guys?
Neighbors.
So they are?
Also
Vicinal. Vicinal, each of them is vinyl. So any two atoms that they are bonded to each other, any two atoms, they are vicinal atom neighbors. That's all it is. So here we have two vicinal atoms that they have at least one hydrogen left. Each of them can lose a proton. That's why we can get two products. And as soon as I wrote it, probably you are correct if you argue with me, why not 3? And then I said, yes, you are right. Because that's very intentionally I used. So you and I don't have to be worried about E or C. Am I correct, guys? This one does not have E or C. Why it doesn't have E or C?
Because the same group.
Two identical, so how can you assign your high or low? Okay, so here we get two products. Now the question is, of the two products, which one is expected to be the major organic product? Would you expect that 2-methyl 2-butene be major, or 3-methyl 1-butene to be major organic product? I said, which one would you expect? I did not tell you for sure it's going to be. Which one would you expect? Remember, relative stability. The more stable, the more chance it has to exist. The more chance it has to form. So,
Professor, internal long chain alkenes are more stable typically than the ones that are.
They always are more stable, not typically.
Okay.
No.
Making sure my
Internal alkenes are always more stable than terminal or external. In cyclic we call them external, and open chain we call them terminal. Internal alkenes, they are always more stable than terminal or external. So here, this is something that we would expect. The major organic product to be the more stable. Now I'm going use vocabulary that from now on you are going to hear. Saxo and op. Basically, it was Professor Zaitsov that he was doing elimination reaction, and this is something he learned from experiment based on the conditions that he was using, guys. He learned that commonly oh, by the way, I spelled his name the way it is pronounced. As you can guess, different textbooks write the name differently. It is a Russian scientist, so I spelled the way it is pronounced. Some textbooks use that. Your textbook, if I'm not mistaken, starts with S, S-A-Y, Saitsov, something like that. But anyway, regardless of the spelling, okay, your textbook may, really don't remember, I'm not going to lie. And I didn't check this morning to see how they spell it, because it is pronounced Zaytsev. That I am sure. Now, according to Zaytsev rule, base induced elimination reactions generally, please notice that is not always, generally give the most substituted alkene product. So that's why according to Zaytsev, the more substituted product. Don't forget, the more substituted is the more stable. So according to Zaytsev, the product of E2 elimination is more stable alkene, for which it is more substituted. Now that being said, I truly don't know how much the lifestyle of scientists have effect on their kind of thinking and the research that they are doing. But Professor Hoffman, of course, he was not using hollow alkene. That's a different story you will see in 118C. But for now, he was looking at elimination. And one thing was, Professor Hoffman had 13 children. So you can probably imagine how his life was around dinner table. And probably all of these, will you please pass that? Will you please pass that? He was saying, okay, if when we are doing elimination, it's going to be as crowded as around my dinner table, what would happen? And if you are scientists, you can go to lab and focus on other things. And he noticed he doesn't get anything like that. So now, of course, they just published the result, guys. We name in their honor to acknowledge the contribution that they have made in science. Honestly, Zaytsev did not make Zaytsev rule. He did research, he published his result. Same thing with Hoffman. But then when we are realizing that they are important, we honor the scientists. We acknowledge by naming something after their name. Then it becomes Hoffman rule. The product, of course, by the way, I have to tell you, I am not coding them. I am writing my version of what they have stated. So that I want to be clear, guys. I am not quoting them because Professor Hoffman was German. By now you know I don't speak German. And Professor Zaytsev, you can guess, was Russian. I don't speak Russian either, guys. So I'm just giving you my version. So when it comes to Hoffman rule, the product of dehydrogenation of alkyl halide or haloalkane, guys. Either alkyl halide is common name. That's why it's not going to be one word, it's two words, all pure halide. Haloalkane is one word. With a hindered base, is the less substituted. Alkene. So here, please be careful. As you see, now base has effect on the paradigm. If your base is not aesthetically hindered, such as OH minus, or any straight chain on pulse side, for which product would you expect to be major organic product? Diester. So we call them just diester product now. We understand this the more stable. On the other hand, if we use a base that has aesthetic hindrance, then we expect major organic product to be Hoffman. Now give me a coupled aesthetically hindered base from 118A.
Well, tert butanide.
Tertiary butoxide.
Butanoxide. I can't read
No.
my own handwriting.
That's okay. Okay, guys. So this is tertiary butoxide. What is the other base?
LDA.
LDA, which stands for? Yes, lithium. That's good starting point. What's the rest?
I don't know.
That's okay. You didn't remember, that's more important. Obviously, as you know, it is ionic, guys, which lithium is your cation, and the whole thing is your anion. It stands for LDA, lithium. Don't forget ionic compound, cation, anion, always the same rule. Di-iso, that's where the D comes from. Di-iso what? Propyl, 3 carbons, diisopropyl. Now A. Amide. If nitrogen is negatively charged, guys, it is amide. It doesn't matter whether it's NH2 minus or as you see. A nitrogen that it is negatively charged is amide. So that's where you get L, D, A. Okay. So these are the two that they have aesthetic hindrance, and they have to be careful. Now this is something that I have to tell you I saw the result of some research that was done, and I will share some numbers with you only for the purpose of understanding the difference. by the way, when it comes to tertiary butyric acid, either sodium or potassium, those are the two commonly counted ions. So the result of the study that I want to, and that, you see, anytime you see notes, it means there are numbers that I have not memorized, guys. That's the only reason. So, because I do not expect you used different bases for this reaction, and as you and I would expect, so I don't need to write here. Carbon. Is this Hoffman product or Zeisser product? Definitely Zeisser, more substituted. And the other possibility would be which obviously is going to be Hoffman. So, are these Z and Z, is that for stereo guys here? Is this Z is for that? So obviously it's not for the stereochemistry, is that right? Because there is no stereochemistry. So let me put rule so you know. Okay, so I'm going to give you a few bases. Of course, they did truly something like 20 different bases. I just picked a few that I can show you the effect of base. First, what would you expect to be major? Z or H? Definitely Z. And that's what they got. They got 79% versus 21%. They used tertiary butoxide. Which one would you expect to be major? Definitely H. They got 73%. Then they used I hope you are noticing what they did. They changed one of metals to alcohol. Now what would you expect happens? H even more. Is that right? You would expect H even more. And that's what happened. And they changed. The 3-methyl with 3-ethyl, they got 99% Hoffman product. So truly, this research showed that what we understand as Zeisser and Hoffman is accurate. Of course, I have not given you the mechanism yet. I know I have promised you for a reason, because I'm saving mechanism for the next step. So, regioselectivity, from now on, anytime, we are doing elimination. We have to pay attention to regioselectivity. Now, whether you call it selective or specific, same thing, guys. There is no difference between calling it regioselectivity or regiospecificity. The two are the same thing. It means that one structure is more favorable than the other one. How many atoms are involved, guys, in E2 elimination from your starting carbohydrates? How many atoms are involved? Total of, say it.
I think 4.
You are correct. 4. Remember, hydrogen and halogens are departing, and 2 carbons that they make carbon-carbon. So there are 4 atoms in it. E2 elimination requires very specific stereo relationship between these 4 atoms. E2 reaction requires very planar geometry. Okay. Now, what does it mean? All 4 atoms must be in the same plane. Okay, guys? By periplanar geometry, it means H, C, C, L. L stands for?
Leading group.
Leading group. The 4 atoms that they are involved in E2 reaction must be in the same plane. Now, as you know, we are using projections in organic chemistry. You already have seen Fisher projection. Am I correct? You have seen what other projection? Newman projection. 3D projection. Is that it? So in OChem, we are using different projections for different purposes. When it comes to periplanar, there are 2 projections. One, I am sure you have heard, Newman. The other one, I'm not sure. Sawhorse. Have you heard Sawhorse? I guess. So these are the 2 geometry. Now Newman projection. So first, I will talk about Newman projection. Remember, in Newman projection, you are looking down the axis of the 2 vicinal carbons. Is that right? That's what you are doing. Front, back. It doesn't matter which one you put front, which one you put back. When it comes to Newman projection, as you and I know, we have 2 extreme cases. One is the one that I have. You call this projection which conformer? Eclipse. And the other alternative would be staggered. I want to remind you, in case you have forgotten, the carbon that you are looking, or the atom that you are looking at, it is the center of your cell. That's why you will see that the bonds are going to go to the center. The one that it is bonded and it is in the back, that's why you will see the bond are not going to go all the way to the center. So be careful. Now, I am going to ask you of these two, both of these are periplanar. Why both of these are periplanar? I hope you make models at home and you see it for yourself. In both cases, the 4 atoms, the 2 vicinal carbon and hydrogen leaving group, they all are in the same plane. By the same plane, I mean literally you can take a piece of paper and put between them, you are going to get 2 equal halves. Or you can take a knife and cut them. You can cut through half of each of these groups. Now, this, we call it SYN, pretty much similar to cis guys. But cis antennas are permanent steady. Remember, conformers are temporary. That's why we call them SYN. SYN periplanar. Based on what you see, what would you call that conformer? N-type. Of course, depends on your nationality, anti or anti. Periplanar. Now I'm going to ask, between SYN and N-type, which of the two is more favorable?
N-type.
Obviously, N-type. Don't forget, when it comes to E2 elimination, you have very, very crowded transition state. So when it comes to E2 elimination, it requires N-type periplanar geometry. The 2 groups that they are departing, they must be 180 degrees apart. Why is that? Because as you can see for yourself, here you have less steric hindrance. It is a lot easier for the base to reach this group, this hydrogen, than the other one. Don't forget, it is too crowded. So that's the reason that base will come, and obviously that is going to be the driving force. Please pay attention to arrow. They are they are not fish hook, they are regular curved arrow, because we are dealing with 2 electrons and your leaving group is going to leave. So this is something that, again, I repeat, we have learned from experiment. That being said, we have to prove. And the nice thing is, with organic chemistry, it is possible to prove certain things. And I will give you an example that it will show exactly what we have believed is accurate. Our understanding is correct. So to talk about it, I'm going to ask you to write major organic products of the reaction that I am going to write. Like major organic product of this reaction. Okay. This is what we have. Yes, how many of you have this? Okay, not many. All right? No. Then let's look at the requirement. Obviously, we have terms. I'm not going to, of course, on exam, if I ask you, name this compound, and you write terms, you are going to get wrong. I'm going to tell you that. And because you have to assign R and S, that is said. But for now, I'm going to use terms because I'm not talking about nomenclature. I'm going to talk about relationship. Obviously, for numbering, you would say 1 boromole 2 methyl. Is that right? Mm-hmm. 1 boromole 2 methyl. Now, one thing that we know, the two departing groups, which are hydrogen and bromine. What should be the relationship? Yes. What should be the relationship between bromine and hydrogen? They have to be 180 degrees apart. It means with cyclic cyclohexane, they have to be in axial position. Equatorial position, they can never be 180 degrees apart. They have to be in axial position, which, as you would expect, is going to be less stable, that it is about 3 kcal. The difference between the two conformers is about 3 kcal. And up to 6 kcal, I always say it is on the house. What do I mean by that? If you are doing a chemical reaction that requires up to 6 kcal, room temperature provides up to 6 kcal. So consider 25 degrees Celsius as heat gas. Okay? So when you are doing the reaction at room temperature, 25 degrees Celsius is providing the 3 kcal that we do need to go from one conformer into the other. So now I have my bromine. Would the methyl group go in axial position or equatorial position on column number 2? to be trans, it has to be opposite. Is that right? Do you have hydrogen on atom number 2 anti to boron? No, don't forget, again I repeat, the required geometry for E2 is anti. With this molecule, there is no hydrogen, it is carbon. Your hydrogen is in a position which is not in anti-position. So you cannot do elimination between these two vicinal carbon. But the other, there is no problem. You have hydrogen that is positioned in anti. So your base will come and take that hydrogen away. That is going to be the driving force to make the living good to live. So that's the reason that here we could not get the Zeiss. There was no possibility to have the right stereochemistry for Zeiss paradigm. On the other hand, what happens if I use the di-stereomer of this compound? So what's the difference if I use everything else is extra? Okay. First, I get two products. Second, between the product on right side and product on left side, for which one would you expect to be major organic product? Definitely the right side, because it is Zeiss. So this time we get two. That major organic product, I don't know if you noticed the size of it. Was a little bit bigger, which I was telling you. This time I have two, that is major organic. Now, why this time? First, I get two products. Let's look at it. Again, the required. Absolutely. This time, both vicinal carbons have hydrogen in anti-position. So your base has choice. If it goes to hydrogen B, guys, you will get the product that I have labeled B, which it is Salzburg. If it goes to hydrogen A, then you will get product A, which it is half. So this is one evidence. Okay, for when it comes to cyclic molecule, it is easy to predict major organic product. A stereochemistry of the product as well. And this time by a stereochemistry, I truly mean a stereochemistry because I have a stereo standard. Not only I'm talking about, my double one, I'm talking about that. That how about open chain molecules? How can I predict what would be the stereochemistry of carbon-carbon double bond? By that I mean, could it be E or could it be C? Now I'm going to write the name of a compound. Yes, are you done with this part? Oh, by the way, now that I am erasing the board, I want you to know workshops that they are going to be started next week. They will start at 11, not at 10. So there is not going to be any more overlap between office hours and workshops. Again, thank you for telling me in time so we can make it. So that being said, now let's start. What should I do? Because I want to use something that has a stereochemistry. 2R, 3S, 2, 3 method. 10. So I'm not going to write the molecule with this R and S. I'm just writing neutral molecule. Am I correct that it is common knowledge? It is not possible for you and I to assign R and S on this molecule. It's only for the purpose of not finding out the stereochemistry of the product. So let's react this one. Again with sodium ethoxide in ethanol. Question. Do we expect E or Z? I'm sorry. Do we expect Hoffman or Zaxxon as major organic product?
Zaxxon.
Definitely Zaxxon. Because both vicinal carbons have hydrogen. So we know, according to our rule, more stable product if you are using a base that does not have a steady element. So if it's going to be Zaxxon product as major, obviously the question is which diastereomer? E or Z? Now, the answer to that is how good you are in drawing stereochemistry of the compounds. Keep in mind transition state requires that the two groups that they are departing, they be 180 degree apart. Now I told you commonly two projections are being used. I gave you one which was Newman. What is the second one? It is sawhorse. Now what is sawhorse projection? Pretty much it is 3D, guys. It is 3D. In sawhorse, you are looking at the bond between your vicinal carbon that they are involved in reaction at an oblique angle, and probably you know the shape of sawhorse. Again, forgive me for my poor drawing. Okay. So what I am saying is, you want the two groups that they are departing, they be 180 degrees apart. Okay. And keep in mind, you are looking at this angle. In this case, you are looking at this angle at this one. Now, those of you that you are good with stereochemistry, obviously you do know you have to put the two departing group in this manner. And of course, again, it won't make any difference. You put your leaving group here, your proton there. Again, won't make any difference. The most important thing is that you have correct stereochemistry. So those of you that you are good with stereochemistry, you will probably do it in 1 minute. You will get your product with correct stereochemistry. But what happens if I really am not secure about my stereochemistry? I'm one of those guys. I will spend 2 minutes instead of 1 minute. What I mean, I will do Fisher projection and change Fisher projection into Newman, then I rotate it, which I'm going to tell you right now. I don't know if you still remember your Fisher projection or if a lot of time was spent on Fisher projection. One thing I'm going to tell you, if I am doing Fisher projection for the purpose of assigning R and S, this is something that I will tell myself I am on the riding seat. Remember, when you are assigning R and S, you are assigning the priorities to the fourth group. Then you will hold the group with least priority to go away from you. And you look at the relationship between the other three. It is clockwise or if it is counterclockwise, S. Now, in Fisher projection, vertical groups means the group is going away. Horizontal means the group is coming towards you. This is something that it is important for us to remember. Now, obviously, let's put carbon number 2 here, carbon number 3 here. Okay. Now, I want to assign R and S. I will obviously put hydrogens there. Okay. Why I put hydrogens there? Because if hydrogens are there, the stereochemistry is what I see. The group with least priority is going over. And that's the whole idea. Now, carbon number 2, you are assigning priority. Probably most of you are used to ABC. Am I correct, guys? For 1, 2, 3, 4, it doesn't make any difference. Keep in mind. ABC or 1, 2, 3, 4. Won't make any difference. So most of you, Volhard Short is using ABC, so that's what we are doing here. Bromine highest, your main chain second highest, and the metal, the C obviously hydrogen always is going to be. For carbon number 3, which group has highest priority? Carbon number 3. You have ethyl, you have metal, you have main chain. Which one has highest priority? Highest. The main chain. A, obviously then B, C, hydrogen. Okay, so I want carbon number 2, Br. So where Br goes, on the right side or the left side? To Br. Because with chain, don't forget, you have no control, it is B. And so the only thing you have to decide is hydrogen and metal. Where do you want the hydrogen goes? Obviously it has to go, it's not where I want to go. Because I want all, A, B, C. Hydrogen is in the back. Okay. Now carbon number 2, I want S, and when it comes to carbon number 2, I know main chain has highest priority, so I want to go there. A, B, C. So this one makes sense. 2R and 3S. Okay, guys. So that's the first thing, right? Now, in Fisher, when we are going to go to two-dimensional, which Newman projection is, Fisher projection is, vertical groups are eclipse position. Okay, guys? So now I want to go from Fisher to Newman. Now keep in mind, going from Fisher to Newman, either I have to look down the axis of carbon number 2, carbon number 3, or vice versa. Carbon 3, carbon 2. So, which one I want to do, I will show you both. So you can see the difference. If I am looking at carbon number 2, I don't want to do it. The other one can. Thank you so much. Sorry about that. Okay, guys, please pay attention. Carbon number 2, my S. Vertical group, and obviously my foot is mentioned. Is that right? Pay attention. I'm looking on carbon number 2, carbon number 3. What happens to the group that is there? Is it going up or down? I'm not going to demonstrate how would happen if you look at carbon number 3 too. Is that right? So that being said, thank you so much. I don't know if it was by accident or you always doing it. It was a perfect. Good. So I'm looking carbon number 2, obviously carbon number 3. So when it comes to carbon 2, remember, if you go carbon 2, you go up. What goes up there, guys? Hydrogen. What goes on the right side? Br. What goes on the left side?
Metal.
Thank you. Now don't forget, they are eclipsed. Is that right? So if they are eclipsed, what is the relationship between the two hydrogens? They are the same.
Next.
Okay. Obviously, bromine and metal are eclipsed. Metal and ethyl are eclipsed. Now what would happen if you were looking down the axis of carbon-3 carbon 2? If you look down the axis of carbon-3 carbon 2, then it would be the other diagram. This is 3, this is 2. Is that right? So hydrogen. That means that everything else is the same. Carbon number 3 has metal on the right and ethyl on left. Carbon number 2 has bromine on right and metal on left. Unfortunately, I'm out of time, so I cannot finish to tell you whether it's going to be E or C. I'm assuming you will show up tomorrow, and we will continue. Have a nice day.
Can I ask you a question real quick? So do you remember what is the Hoffman and the shape
that
of it?
vertical
Do you know what the definition of it? Because when we're choosing the major product, I don't even know which one is Hoffman and which one is.
Yeah, I'm not sure about that, but the more substitutes is
because that one, these look like the same to me. Because you can also
If that's okay, so
yeah, I'm not sure about it.
Okay. Well, thank you.
Do you know when is the workshop?
Next week.
Next week?
Yeah.
At 7?
I'm
not sure.
I'm not sure, but it's saying next week. We should probably mention that later.
we rotate it, so now they're in different places. Okay, thank you.
That is strictly used.
There's definitely some people are better at spatial, at imagining rotations than others, and it's kind of a feeding aspect. I'm not particularly.
Yeah, that's of course, don't forget, I have also 10 to 11 guys. Like I said back here. Okay.
I found that lab tends to be stressful enough that high score on the test because we're trying to lab at the same time again.
I'll have to ask you that question because I see.
The results tired me out because I'm clumsy and I
Keep in mind,
I can never
you are happy with
I was
that
always like,
if it was
I was always like the last.
80 or higher. If you are happy, then the order of course is
I'd rather have the time to study.
Yeah, I accept
get
it.
a decent score on the exam.
Then you have the ACC that to me.
Then we get tired to study and get shit scores on the exam.
Living my care, so it tells you I need variety.
I got really confused, I guess.
People slowly.
to be honest, right now, we have talked about it. Because if you had asked me 3 years ago, I would say almost none. And now I would say
So you did go to legislature. And today. Oh, you are going today. Yeah. Make sure before you add the new section, drop your old section. So you will get
I swapped the section. They have an option to swap it.
Exactly.
Yeah.
Oh, good. So you did already.
Yeah.
Oh, good. Good.
Thank you. You remember?
Yeah. I said I think that they affect students. I said I should remember to investigate. So this is because I'm there to help them now.
You have a good memory. And when is the workshop?
It's starting next week.
You know the time?
If I'm not mistaken, it is Tuesday, Wednesday, Thursday, 11 a.m.
At the
Where it is student assessment. Okay.
Thank you.
Workshops are in Dorchester.
With the big like room upstairs in the second floor, I think.
Thank you.